Great. So now we will start on the second part of Lecture 1, now looking at how we model materials. We do this in a preliminary way. We'll do this much more in a later lecture. But this introduces what we're shooting for is the development of what's called the constitutive relations, relating the magnetic fields to the magnetic fluxes, the E to the D, electric field E to flux density D, and the magnetic field H to the magnetic flux density B. So, let's look at the electric field first. Materials are modeled as an array of molecules that can be electrically polarized, i.e. being dipoles, or becoming dipoles in the presence of an electric field. We need to build up a macroscopic model of this. So we write down and we get a chunk of material and we split up our material into cubes. D3 are volume elements of the material that will have a certain amount of a dipole moment with respect to that cube, a total lowercase p. Now, we introduce a dipole density in this way, where we say our dipole density is such that it's, when dotted into the D3R, that it is equal to, or multiply with it, it is equal to lowercase p, the dipole moment of that cube. So this defines dipole density. So we have the potential produced by this dipole, we had derived it earlier, is just simply equal to this right here. Now, we only had V on this side in an earlier slide, but now this is only a small component of the overall total potential produced at observation point O due to this D3 of volume over here of dipole. So we substitute this right here in for lowercase p, and we have this. Now, next we're going to work on this r hat over r squared. And we note that a math a math result, a math formula, our identity, gives you that the gradient of the function 1 over r is equal to this r hat over r squared. So we can replace this part right here with del 1 over r. Now, another formula, identity, property, is basically the product rule, where we have del dot f, a function times vector a. You can do this operation of del dot separately. You get f del dot a dot del f. And so we can then arrange this and solve for this side, a dot del f, in terms of this. That basically means our f is going to be the 1 over r, and then the a is going to be our p. And we're going to use these two results to express that potential in terms of this right here. All right, where we have the del dot p over r minus del dot p over r outside that operation. Now, so what we see here is that we have a del dot something, that's our entire integrand, so we can use the divergence theorem to change that from a volume integral over to a surface integral. And when we do that, we get the p dot ds, but we pull out the normal vector, we pull out the vector aspect of our s and write it as ds scalar times ns vector. This is the normal component of this infinitesimal surface element along our surface that we're integrating over. We have p dot n hat s. All right? So this is over the surface of our material. But this right here stays as an integral over the overall volume. And we have something that looks like potentially a charge particle, individual little point particle, because we have the 4 pi epsilon naught r in the denominator. That would match the potential produced by a point charge. But in this case, we don't have rho up here as we would have for individual point charges. We have a minus del dot p. All right. So and same thing here. We have the 4 pi epsilon naught r, but instead of a rho here or a charge element, charge density, we have a p dot in s. So these must represent charge densities over the surface and throughout the volume. And so that's what we define these two quantities as. P dot n is equal to a charge density, namely a surface polarization charge density, and the minus del dot P, capital P, is equal to a volume polarization charge density. So when we polarize a material, whether it's inherently polarized, naturally polarized, or if we induce polarization due to a applied electric field, we are in effect producing charges within that material that can then produce its own electric field, that can produce a electric potential, and so forth. And so one good thing to do is to verify that if you started with an initially charge neutral material, the fact that you may have polarized it with an electric field or something else shouldn't affect the overall charge. You've just separated charge within that material. So you should have charge conservation. So if you add up all the surface charge, and if you add up all the volume charge, and add those two things together, you should get 0. So even though you have polarized material, you haven't added or taken away electric charge of that initially neutral material. All right, so now we can go back to Gauss's law. And we can say, okay, del dot E certainly is rho total over epsilon naught. That's the most fundamental law, that to get the electric field, you take all the charge elements, add them together, divide through by epsilon naught, and that gives us the divergence of E. But now we can split this rho total up into two different types of charges, charge densities. One that's free to move everywhere in the material, or externally inputted into the material above and beyond what we have in the molecules. And then a charge, concentration or density that's produced by the polarization of the molecules within the material. And that's this right here. So we separate those two things. A free charge or externally applied charge, and a bound charge, a polarization charge. All right? And so then we can solve for this. We can take this over to the other side, multiply through by epsilon naught, and we get this right here. All right? Now, this was our polarization charge density. That was, going back up to here, this right here. So we substitute this right here for this, and the negative goes away. We get the del dot P. We have two del dot operations in the first two terms here. We take that out, and then we have epsilon naught E plus P. And so we now call this, we define this sum of two different vectors, electric field and polarization charge, polarization density, as electric flux density, sometimes called the electric displacement. So, some books call it entirely electric displacement. Other books call it entirely electric flux density, and some books call them both. But this is del dot D is equal to the free charge, the charge that's free to move, not bound, not polarized, or charge that's externally applied to the system. Thus, D affects only rho v and vice versa. It only interacts with rho v. Now, often P is linearly related to E, meaning that the greater the externally applied field, or the total field, actually, the total field, the greater the amount of polarization of the material. this makes sense to a certain degree, mainly up to a certain strength of E. After a certain strength of E, either the amount of polarization that you can do, the separation of the positive and negative charges within a molecule, maybe that you can no longer do that, and it just, regardless of how much stronger the electric field is, it won't polarize it anymore, separate those charges anymore, or potentially you just rip the charges apart. And so in that case, you go to a nonlinear regime for the relationship between P and E. But as long as you stay away from that, you can assume that P is linearly related to E in this way, right here. So when you plug that in, then to the equation above, to this equation here, you get D is equal to epsilon naught E plus P, which was, we're expressing it as chi epsilon naught E. And you take the E out, and then you have this term right here, which we lump together in the term we call epsilon, which is called the permittivity of the material. Permittivity of the material. And it involves the way the material reacts to an applied electric field, to a total electric field. Often what we'll do, almost all the cases, is that we'll express epsilon in terms of epsilon naught, the permittivity of free space, times a unitless number. And this is whenever you it's called the relative permittivity, or especially the dielectric constant. And so this is where, if you just ask what's epsilon for glass, for example, and we would say something like 2.1. And that's when there's no units and it's like 2.1, you know that we're giving you the dielectric constant, or the relative permittivity, instead of something like 16.3 times 10 to the minus 11, which would be the permittivity for glass, times 10 to the minus 11 farads over meters. If it's 2.2, 2.1, or if we don't specify, it's the relative permittivity or the dielectric constant. So this is the all-important permittivity that connects flux to field. All right. Now, likewise for magnetics, we lump all of the molecular current loops together as a collection of magnetic moments. So each molecule, each atom, will have their electrons rotating around the nuclei of the atoms, creating current loops. Those current loops are called magnetic moments. They produce a magnetic moment, similar to the electric dipole moments. And we then model the magnetic behavior of the materials by looking at an array of these magnetic moments, these circulating electrons around their nuclei. The total field is then produced by the fields produced by any free current that we have in the material that's not a result of the motion of electrons around nuclei, and by the bound currents, or the current produced by the electrons rotating around the nuclei. And so we take Maxwell's equations, Faraday's law, and Ampere's law, and we have del dot, and then we put in here the magnetic flux density, B over mu naught. We define this new quantity here, and we say that then is going to be equal to the total current, JF plus JB. This is the total current. And the total current, JF, this is composed of the free current and the bound current. Now, the free current we assign to be related to the magnetic field by being the curl of the magnetic field. So JF is equal to del cross H, whereas JB is equal to del cross M, where M is the magnetic dipole density. Now, with del being for both this term and that term, we take it out, and then we have H plus M. We have del cross, we have del cross, so therefore B over mu naught must be equal to H plus M. We take the mu naught over, and we get this relation that B is equal to mu naught H plus mu naught M. Thus, it is H that affects JF, and vice versa. H that affects JF, and vice versa. Not B. B is indicative of what's going on with the total current. So this is different because this is the field, this is the flux. H is the field, B is the flux. But it's H that is affected by and affects the free current, whereas B is affected by and the total current. And this is different than it is in electric fields and fluxes. It's interesting that it was done that way, but that's the way it's done. So just like when in electric fields and polarization, the M is linearly related to H quite often. And we write it like this: N is equal to chi M sub H, where chi M is called the magnetic susceptibility. Thus, we have B is equal to mu times the quantity 1 plus chi M H. And therefore, we express mu naught 1 plus chi M as mu, where mu is a magnetic permeability. And it can be expressed as mu is equal to mu naught mu R, where mu naught is a permeability of free space, 4 pi times 10 to the minus 7 henries, and mu R is the relative permeability. Thus, we now have the all-important constitutive equations that connect the fields to their respective fluxes. D is equal to epsilon E, B is equal to mu H. So now we're getting to the goal of patterned materials, or composite materials, or metamaterials, or engineered materials, or a variety of other terms people use to say materials that may not exist in nature, but we want to have epsilon and mu have particular values on a point-by-point basis in a material, on a surface, along a line, or something. And so we want to engineer epsilon and mu to be something that turns out to be useful for a particular application. Sometimes you want epsilon to be positive and mu to be positive. In that case, we have naturally occurring materials that have epsilon positive and mu positive. Those are dielectrics, those are glasses, those are semiconductors, quite often, as long as, semiconductors. We have epsilon that's negative and mu positive. Those are metals in the optical regime in IR. And we even have materials that have mu negative but epsilon positive. Those are called magnetic plasmas. But in nature, no one has discovered a naturally occurring material that has both epsilon being negative and mu being negative. And so this was something that no one had ever, and to this day has ever found, a naturally occurring material with both epsilon and mu being negative. This was when Victor Vezlago, back in 1967, said, wouldn't it be neat if nature did provide such a set of materials with both epsilon and mu being zero? What would that allow for? And then he wrote this famous paper that said, well, if we did have these types of materials, it would allow for perfect lenses, for the compression of light in extreme ways, of the localization of light at surfaces, all sorts of really interesting things. And then he spent the rest of his career trying to find naturally occurring materials that have negative epsilon and negative mu, only to fail. And it was only in 1999, I think, but after that, when two researchers said, okay, we've given up with trying to find a naturally occurring material, let's engineer man-made materials that would have these parameters. And I'll cover that a lot more later on, but that was the birth of metamaterials. All right, a couple last but important things to say. First of all, energy density. We've sort of went right past that. We could have introduced this back when we looked at electric fields and electric potentials, but we sort of needed those constituent relations first before we can dig into this. So I'm not going to go through the detailed derivation. It's really simple. It's in Griffiths, it's in Sadiku, about how you figure out the amount of work necessary to put together a certain charge configuration, charge by charge. And the amount of work necessary to do that, to bring various collection of charges together is equal to this. It's equal to the sum of Q times the growing amount of potential in the system. And this. And then typically what you immediately do, you turn this into an integral. So this sum, you let Q be equal to rho dV, so Q is equal to charge density times infinitesimal volume, and this is V, and you integrate over the volume. All right, and in rho from the Gauss's law in materials is del dot D. You put that in, and this is what you get. All right. Using this mathematical relation, again, basically the product rule, you can change this right here over to this 1/2 the integral of del dot B D, where V and D are in the del operation. Thus, you can use the divergence theorem to get this volume integral turned over to a surface integral. So this is the surface energy, And this integral right here, if you take the minus sign in right here, you have minus del V. Well, that's simply the electric field right here. So we have this right here. Now, there's nothing more you can do with this. So this stays as a volume energy. So this is the energy in the volume of the material, and this is the energy at the surface of the material. Thus, if you take the 1/2 in here, 1/2 inside the integral, then this is the amount of energy per infinitesimal volume element, which is really the energy density. So this is capital W, this is lowercase w. So this represents energy density, is the integrand, the 1/2 d dot E. So this is, if you have a certain field, electric field, and you have a certain flux associated with that, D, then the energy density for that field is this. With the constitutive relation, you can express this as D being equal to epsilon E. You can express this as epsilon magnitude E squared over 2, or 1/2 epsilon magnitude D squared. And so just the field itself will contain energy. And most of you know that, but just this is the formula for that. Now, same thing with magnetic energy density. You have a very similar result. 1/2, instead of D dot E, you have 1/2 B dot H, which with the magnetic constitutive relation, you can express it in either of these two forms, and that's that. Now, why it's important is because quite often in the simulation profiles, you're looking at resonant modes. And you can discern, you can identify a resonant mode when you plot out the energy densities of the fields, and then you will see a very large energy density, and that will tell you basically that you have a very large field in those locations, and you've tapped on a resonant mode. And those tapping into resonant modes is very important in pattern materials, because quite often at resonances, or where you have high built-up field energy densities, those are the locations where you have the useful optical or electromagnetic properties you're trying to have your system exhibit. And so knowing that fact about magnetic fields and the relationship between magnetic fields and energy is good once we get into the job of doing the pattern material design in engineering. There's a whole host of things I've skipped in this review. And you go back and say, well, I definitely have to go over that, and definitely have to go over that. But I've covered in these first two videos the absolute necessary stuff for the pattern materials that we'll get into later, at least the statics part of it. We're going to go over the waves, the diffraction, the boundary conditions in separate videos. But there are a variety of other things that you could say, well, you skip this and skip that, and that's true. And I very well may add particular subsections to this or addendums to this video. For example, not the Lorentz force law is just sort of rounds out the basic equations of electromagnetics. So besides the Maxwell's equations and constitutive relations, the other major formula that's attached to that page that lists all the important formulas of electromagnetics is the Lorentz force law. So you should all sort of know that, even though that won't come in all that much in us designing devices at all, really. But something certainly that I skipped over just for the sake of time, and also because it was very analogous to our treatment in electrostatics with its scalar potential. Magnetics doesn't have a scalar potential, but it does have this magnetic vector potential. And with that vector potential, then you can go and calculate and derive the magnetic fields and magnetic vector potentials for magnetic dipoles, the current loops, and that is necessary then to look at the magnetic properties of materials. So this is an important section 2 that you will want to review, and so you may also want to look at that. So, but understanding the various relations within these two videos on the electrostatics and magnetostatics, and I will be assigned, and then I will, in a note, in an email, talk about the sections in Griffiths that covers this. All right, but it would be electrostatics and magnetostatics for any textbook that you would use. And then I'll assign a smattering of homework problems that gets you to exercise the various concepts, your knowledge in the concepts that I've covered. And I'll do that later this evening or so. Okay, so this is our first video of many, and we will be holding question and answers. With such a small group, we can even do things like a Google Chat or a Skype or something of that sort. And so we'll all, as this develops, this course develops, figure out the best way to get some feedback on the concepts, to do questions and answers, and to do various things of this sort. So that's it for lecture 1.